Banded iron formations. Banded iron formations are distinctive layered sedimentary rocks primarily composed of iron-rich minerals interbedded with silica-rich layers, chert. They are some of the oldest rocks on Earth, dating back to the Precambrian era, specifically from about 3.8 to 1.8 billion years ago. BIFs are significant in geology and Earth history for several reasons, including their economic importance as major sources of iron ore and their implications for the understanding of the early Earth's atmosphere and biosphere. Composition and structure. BIFs typically consist of alternating layers of iron-rich minerals, such as hematite and magnetite, and silica-rich chert or jasper. The iron layers are usually dark and dense, while the silica layers are lighter in color and can vary from white to red, depending on the presence of other minerals. The banding pattern in BIFs can range from very fine, millimeter scale, to quite coarse, centimeter scale. Formation and geological significance. The formation of banded iron formations is closely linked to the conditions of the early Earth's oceans and atmosphere. There are several hypotheses regarding their origin, but the most widely accepted theory involves the interaction between ocean water and atmospheric oxygen produced by early photosynthetic microorganisms, such as cyanobacteria. During the Archean and Proterozoic eons, the Earth's atmosphere contained very little free oxygen. The oceans, however, were rich in dissolved iron. Oxygenation and precipitation. As photosynthetic microorganisms began producing oxygen through photosynthesis, the oxygen released into the oceans reacted with the dissolved iron to form insoluble iron oxides, which precipitated out of the water and settled to the ocean floor. This process created alternating layers of iron-rich minerals as conditions fluctuated, with periods of high biological activity producing more oxygen and thus more iron precipitation. Chemical cycles. The periodic banding observed in BIFs is thought to reflect cyclical variations in environmental conditions, such as changes in biological activity, ocean chemistry, and climate. These cycles could be seasonal, linked to changes in the availability of nutrients or sunlight, or longer-term, driven by geological processes like volcanic activity. Economic importance. BIFs are economically significant because they represent some of the world's largest and richest iron ore deposits. Major iron mining regions, such as the Pilbara region in Western Australia and the Mesabi Range in Minnesota, USA, are underlain by extensive BIFs. The extraction and processing of iron from BIFs have been crucial to the development of modern industry, providing the raw materials needed for steel production. Paleo-environmental and biological insights. The study of BIFs offers valuable insights into the Earth's early environment and the evolution of life. The presence of banded iron formations indicates that there were large-scale oceanic and atmospheric processes in operation over 1 billion years ago. The oxygenation events recorded in banded iron formations mark significant milestones in Earth's history, known as the Great Oxidation Event around 2.4 billion years ago. This event dramatically changed the composition of the atmosphere, paving the way for the evolution of aerobic, oxygen-dependent, life forms. Furthermore, banded iron formations provide indirect evidence for early microbial life, specifically photosynthetic organisms like cyanobacteria. The oxygen these organisms produced not only led to the formation of BIFs but also played a crucial role in shaping the planet's habitability. Modern implications and research. Ongoing research into BIFs continues to refine our understanding of ancient Earth processes and the conditions under which they formed. Geologists and paleobiologists study the isotopic composition, mineralogy, and microfossils within banded iron formations to reconstruct ancient environments and biogeochemical cycles. This research not only sheds light on the history of our own planet but also informs the search for life on other planets, where similar banded formations could indicate past or present biological activity. In summary, banded iron formations are not only key geological records of the Earth's early history but also crucial resources for modern industry and important windows into the processes that have shaped our planet and its biosphere over billions of years. Properties of banded iron formations. Banded iron formations are unique and complex sedimentary rocks that exhibit a variety of physical, chemical, and mineralogical properties. These properties provide crucial insights into their formation processes, geological significance, and economic importance. Here is a detailed overview of the key properties of banded iron formations. Physical properties. Layering and banding. Appearance. Banded iron formations are characterized by their distinct alternating layers of iron-rich minerals and silica-rich chert. These layers can vary in thickness from millimeters to centimeters and can be very regular or somewhat irregular in pattern. Texture. The texture of BIFs ranges from fine-grained to coarse-grained. The iron-rich layers tend to be denser and harder, while the silica-rich layers are generally finer and more brittle. Color. Iron-rich layers. These layers are typically dark, with colors ranging from black to dark gray due to the presence of minerals such as magnetite and hematite. Silica-rich layers. The chert or jasper layers can be white, red, or light gray. The red coloration is often due to small amounts of hematite dispersed within the silica. Density and hardness. BIFs are generally dense rocks due to the high iron content, which makes them heavier than many other types of sedimentary rocks. The iron-rich layers are quite hard, whereas the silica-rich layers are relatively softer but still hard due to the presence of microcrystalline quartz. Chemical properties. Iron content. Composition. Banded iron formations have a high iron content, which can range from 20% to over 60% by weight. The primary iron minerals are hematite and magnetite, with lesser amounts of siderite and other iron-bearing minerals. Economic importance. The high iron content makes BIFs a major source of iron ore for industrial purposes, particularly in steel production. Silica content. Composition. The silica-rich layers in banded iron formations are primarily composed of microcrystalline quartz, known as chert or jasper. These layers can contain impurities such as iron oxides, which impart color variations. Purity. The silica in banded iron formations is often very pure, with minimal contaminants, making these layers highly resistant to weathering and erosion. Trace elements. Banded iron formations can contain trace amounts of other elements, including manganese, aluminum, and phosphorus. These elements can influence the color and chemical behavior of the formations. Mineralogical properties. Iron-bearing minerals. Hematite, a common mineral in BIFs. Hematite is an iron oxide that forms reddish to black crystals and is highly magnetic. Magnetite, another primary iron mineral in BIFs. Magnetite is magnetic and forms black, opaque crystals. Siderite, a less common iron carbonate mineral that can be found in some BIFs, particularly those that have undergone less oxidation. Silica minerals. Chert, a fine-grained, microcrystalline form of silica that forms the silica-rich layers in banded iron formations. It is typically hard and brittle. Jasper, a variety of chert that is red due to the inclusion of iron oxides. Accessory minerals. Carbonates. In addition to siderite, other carbonate minerals like calcite and dolomite can be present in minor amounts. Sulfides. Pyrite and other sulfide minerals may be found in small quantities, indicating reducing conditions during formation. Geochemical properties. Isotopic composition. The isotopic composition of oxygen, carbon, and iron in banded iron formations can provide insights into the environmental conditions at the time of formation. For example, variations in oxygen isotopes can indicate changes in ocean temperature and chemistry. Redox conditions. The presence and relative abundance of different iron minerals in banded iron formations reflect the redox conditions of ancient oceans. Hematite and magnetite formation indicate periods of oxygenation, while siderite suggests more reducing conditions. Geophysical properties. Magnetic properties. Banded iron formations exhibit strong magnetic properties due to the presence of magnetite. This makes them easily detectable using magnetic surveys, which are commonly used in mineral exploration. Seismic properties. The density contrast between iron-rich and silica-rich layers in banded iron formations can create distinct seismic reflections, which can be used to map the extent and structure of BIF deposits. Summary. Banded iron formations are complex geological structures with a unique combination of physical, chemical, and mineralogical properties. Their distinctive banding and high iron content make them not only a critical source of iron ore but also an important window into the Earth's early environment and the processes that shaped our planet's geochemical cycles. The study of banded iron formations continues to provide valuable insights into ancient oceanic and atmospheric conditions, the evolution of early life, and the geological history of the Earth.